Hi. So previously we were talking about congruences on integers. Now we have given some definitions and propositions. Then we have did some arithmetic with congruences. Now we are going to talk about that how to solve congruence equations. So let's do that. Okay. So let m be a positive integer and a comma b are integers. Consider the equation ax is congruent to b mod m to be solved for x in Z. Okay, now such an equation is called linear congruence equation. Okay, what does such an equation have a solution? When does such an equation have a solution? Let's find out by solving an example. (13.7) and that says that one, consider the congruence equation. That is 4x is congruent to 2 mod 28. Okay. Now, if x is in Z, is a solution to this, then 4x is 2 plus 28n for some n to be an integer, which is impossible. Impossible, since the left-hand side is divisible by 4. Okay. Whereas the right-hand side is not. Okay. So this congruence equation has no solution. Perfect. Let's consider 2. Number 2 is, now consider the equation that 13x is congruent to 2 mod 31. Now we will show that this equation have a solution, so that observe that HCF of 13 and 31 is 1. Hence, by proposition 10.3, there are integers s comma t such that one can be written as 13 s plus 31 t. Therefore, thirteen s is 1 minus 31 t, which implies that that 13s is congruent to 1 mod 31. Multiplying this congruence by 2, we get we get 13 into 2s is congruent to 2 mod 31t. Which implies that 13s is 1 mod 13. Okay, there should be some space. This is just vertical space. Okay. This implies or means 13s is 1 mod 31. Now, okay, which I have written here. Right. In other words, x is 2s is a solution to the original congruence equation. Now here is the general way of result. General result is proposition 13.86 says that the congruence equation AX is congruent to B mod M has a solution X and Z if and only if HCF of A comma M divides B. Okay, we'll give the proof for this one. So if we prove this, right, D is the HCF of A comma M. Okay, now first let us prove the left to right implication. So then we prove this implication. So suppose the equation has a solution X and Z. Okay, then suppose the equation has a solution X and Z, then AX is QM plus P for some Q in integers. Now since D divides A and D divides M, it follows that D divides P. Now, for this part, suppose D divides B, say B is KD by proposition 10.3, there are integers S comma T such that D is SA plus TM multiplying through K gives B is KD, which is K into SA plus TM. Hence, AKS is B minus KTM is B into mod M. And in other words, you're saying X is KS is a solution to the congruence equation. This will prove the proposition. Okay.